Okay, we're on page 108.
It's even Korean Navy, bro.
Okay, we're talking about the Aufbau principle today and two other principles, the Pauli exclusion principle, and what the next one is not a principle, it's Hund's rule. So two principles and a rule. You already know about the Aufbau principle, okay? There's nothing new about it. It's just that you fill up lower energy levels before filling up higher energy levels. And so you can follow the energy levels like this, 108. The diagonal rule, 108. Actually, we're on 109 now. I just threw these in here because I really liked all these periodic tables, okay, because they actually show you all the 1s, the 2s, the 2p, the 3s, the 3p. So if you like these, you can refer to them. One nice thing here, oh, and there's a typo, I see, because whatever row number it is, N is the energy level, and basically N in this case can also be the row number. So in the D subshell, we know that the D's lag one behind the row number, which means that we are in the N-1, row number -1. And the F should be, this is my typo here, it should be N-2. Okay, so that is a typo. I would like you to go there and fix that. This is on page 109. Fix. Hopefully all of this is starting to seem very familiar. So it's the row number -2. By the way, were there any questions from yesterday's homework or the day before or anything like that? Nope. Okay. And then this one is just the long form, which shows you where the F fits in. And that was the Aufbau principle. And now we're going to look at the Pauli exclusion principle. Have you heard of the Pauli exclusion principle before? It came up in the POGL, I believe. Okay, so it's a good thing we're reviewing it, because obviously it made a huge impression on you. The Pauli exclusion principle is another rule of filling orbitals. It's not really the second, it's just one of three, but I'm calling it the second. The first one was, what did we call that first one? Where you have to fill in the lowest ones first. That's called the Aufbau. Pronounced off, bow. Bow is in, not bow. How can I show? As in cow. Aufbau. Okay, so Aufbau. stands for, it's literally from the German meaning building up or construction. Okay, at least that's what I am told, and I believe them. I should really check with our business ed teacher. I cannot remember her last name, but she's German. Pardon me? Yes, probably. Anyway, because she speaks German. Now we have the Pauli exclusion principle, and this says that electrons in the same orbital cannot have the same spin. So if they are in the same orbital, they cannot have the same spin. And I think you probably know this already. It just means that the arrows have to point up and down. Okay, so if we have hydrogen, obviously there's no pairing. You can draw it either up, which is correct, or down, which is correct. It's unusual, but you can draw it down. Normally we do up first. Helium, we could do up, down. That's good. We could do down, up. That's good. But you are not allowed to do up, up, or down, down. Okay? Lithium, again, if you were to do it this way, this is unusual, but technically correct. And the configuration, of course, we have our 1s. It contains 2 electrons, so it's 1s2, and the 2s orbital contains 1 electron, so that is our 2s1. So far, so good? Okay. Beryllium, we have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. It's got 4 electrons, so it's 1s2, 2s2. That gives us 2 plus 2 is 4 electrons. Yes? Are we allowed to go down, up? Yes. Are we allowed to go up, up? No. Down, down? No. Why not? Yes, because according to the Pauli exclusion principle, according to the Pauli exclusion principle, 2 electrons in the same orbital finish that sentence for your neighbor. Anyone want to donate the answer on that one? Yeah? Yes, very good. Cannot have the same spin. In fact, that's not really what the Pauli exclusion principle says. What the Pauli exclusion principle really says is that no 2 electrons in an atom may have the same 4 quantum numbers. But AP no longer covers quantum numbers, so we're going to pretend that we never heard that, okay? La, la, la. Okay, boron. What is the configuration for electron configuration for boron? It's going to be 1s2, 2 electrons in the 1s, 2s2, and then 2p1. That gives us 2, 4, 5 electrons. Boron is atomic number 5, so it has 5 electrons. That's great. And it doesn't matter whether you put that electron in the first box, in the second box, in the third box, or if you put it upside down in the first box or the second box or the third box. What does each box represent? Tell your partner. And if you didn't hear it, Tony said, orbital. What does this set of 3 boxes represent? What does it represent? The subshell. And if I wanted to highlight yellow my energy level 1, what would I be highlighting? If I wanted to highlight my shell number 1, what would I highlight? Only the 1s. Okay, that's energy level 1, shell number 1. And what if I wanted to highlight shell number 2? What would I highlight? Tell your partner. Now, the reason I didn't do any of the rest of them is because these are all or. Yes, I'm just showing different ways it could be configured. But this here, energy level 2, shell 2. Are we starting to get really comfortable with the terms shell, subshell, and orbital? Yep, good. Energy level, sublevel, and orbital. Good. All right, so that's the Pauli exclusion principle. No 2 spins in the same direction in the same orbital. Hund's rule is our 3rd rule of orbital filling. And that is that electrons fill up orbitals in a subshell singly. That means 1 in each before they start doubling up. And it doesn't just say that, it says they have to be in there singly, but all the spins have to be what? Same direction. So you guys knew these rules already. You maybe just didn't know what their names were. Yeah? So this is Hund's rule. All the spins have to be in the same direction. So let's take a look at it before pairing up. Basically, it maximizes the same spins. I don't know why that's a good thing, but apparently it is. Okay. So here is Hund's rule. And this would be, first of all, tell me, can you figure out which element this would be? This one here. This one. Although the second one is the same, it's just incorrect. That is carbon. How do you know? 6 electrons. Carbon is atomic number 6. Now, so this is carbon. And it is correct to put them in separate orbitals. What is wrong with this one? It disobeys Hund's rule that says they go in singly. Now, it's not that this is an impossible state. It's just not a ground state. Not impossible, just not ground state. So what would it be? If it's not ground state, it would be an excited state. Because those 2 electrons happen to be in the same orbital, they do repel each other a little bit more, so that is less stable than it being in a separate orbital, okay? Electron-electron repulsion in the same orbital. Makes it less stable. So here's just another illustration of Hund's rule. Okay, that's our good one. Is this one here? Hang on, let me shade it in maybe blue so that we can say that one, the blue one. Is the blue state impossible, or is it just not ground state? It's an excited state. Yes. Oh, probably not very much, because it's not like it's up a whole level or something like that. It's just a little bit. So I'm guessing maybe infrared or something lower. I don't know for sure. Okay. And is the one right after the blue one, is that impossible or just not a ground state? I believe it's just not a ground state, but I don't know for sure. I think it's just not a ground state. Yeah, which is more stable than the spin spinning in opposite directions. So I believe that this is the case. I don't think that question is ever going to come up, though. Okay? I would say this one could come up, but probably not this second one. Do you know what I mean? Now, I'd like you to contrast this not impossible, just not ground state with the Pauli exclusion principle. That there, with the 2 spins the same, is that impossible or just not ground state? It is impossible. Nature just doesn't allow it. Okay, when you solve that wave equation, there are 4 numbers in that wave equation that are solved for, and the spin up and spin down have to be different from one another. They have to be. It's a mathematical thing. Okay, so those are our 3 rules. The Aufbau principle. Who's the other principle? Pauli exclusion principle. And finally, we have Hund's rule. Okay. So here's just a few little things here. We have carbon. If we write its electron configuration, it would be 1s2, 2s, 2, and then 2p, 2. And you can see it's okay as long as those electrons are separated from each other. The 2p electrons are separated, and all the spins are the same. Nitrogen has 7 electrons. Please fill them in and write the electron configuration. You can check your answer with mine there. And if you've got nitrogen, you can try the ones down below. Vanadium, iron, and germanium. You are given the number of electrons for each of them. Yes?
So each of the orbitals, right? You have to put the up arrow at the down arrow.
Yeah.
You can like switch it up.
You can go down up,
Yeah.
but you can't go up, up, or down, down.
Yeah,
okay?
But like, let's say on one axis, but like the left one is up and the right one is down.
Yeah.
Can I do on the 2s, the left one is down?
You could. It's considered kind of weird, though. Do you know what I mean? I wouldn't do it just because it's weird. But yeah, I think it's fine. You know what I mean? Yeah. It's fine, but strange. So given vanadium's electron configuration, and given that its last 3 electrons go into the 3D subshell, where would you expect to find it on the periodic table? In what sort of area? Vanadium. Its last 3 electrons go into the 3D subshell. It's going to be a metal. What kind of a metal? It's going to be a transition metal, because the transition metals are where the D subshells are being filled, okay? And if you were at the transition metals and you were counting along the groups, what group would it be in the transition metals? The first transition metal group, the second, the third, the fourth? Which one would it be? It would be the third one, okay? And you can look on your data pages and you can see that, right? Here we have vanadium. It's the 1, 2, 3rd transition element along in that first row there of the transition metals. Okay, good. And if you're not really sure 100% how you're doing these, I would always fill in my p orbitals. Like right now I have 2, 4, 6, 8, 10, 12. I would go 13, 14, 15. I would not fill them in 13, 14, 15, right? Because I might if I end up ending in there, I might end up with the wrong configuration. Does that make sense? So always fill them up singly first and then pair them up. Oops. And if I were feeling lazy about germanium, and I didn't want to write out the whole thing because that's starting to look like really big and long and awful, what could I do instead? I could use the noble gas configuration. So I would get up to, this is my previous noble gas, who would be argon. For S2, 3D10, 4P2. Is good? Okay. Now, on the next page, I just want to show you various options that are available to you in showing the diagrams. This is what we've been using up till now, where we have our potential energy going upward, but sometimes that takes up too much room. So you might just be asked to do them horizontally, where we have our increasing energy going to the right. Yes? You can be asked to do your expanded electron configuration. It is unlikely that you will see this, but do you see in the expanded configuration, we've actually separated out the 2px, the 2py, and the 2pz. I don't think you're going to have to do that. I don't even think you're going to have to recognize it, but I have come across it. So I thought I would just mention it. It usually just gets reduced into 2p6. Is that good? Okay. Just so if you see it that way, you won't be like, wow, what's that? Okay. Of course, our noble gas configuration here is neon. Whoops. That's neon there. And so neon 3s1. And if you're interested in all the electron configurations, you can see them all the way up to krypton. What's that? Oh, there are a couple of exceptions to the rule that you are not expected to know. Okay, so chromium and copper, it turns out that the way I always learned it is a half-filled D shell is particularly stable. And so one of the electrons will get promoted from the 4s to the 3d. However, apparently that explanation is not correct. So that information is no longer on the AP exam. You do not need to know the exceptions to the Aufbau principle. Not because they're wrong, but because the explanation for them is wrong. They've taken them out of the curriculum. So you don't need to know them. If you had chromium on the test, which they're not going to give you because it's an exception and they're not going to give you the exception, you would get rid of this one and put it here. Yeah? That's what you're expected to know. You're not expected to know the exceptions. However, I believe in university they will probably want you to know the exceptions, but you can learn them at that point. Okay, I'm not going to go into them. These are a couple of exceptions you don't need to know. Okay, and there's a whole bunch of exceptions like that in the Fs as well. Okay. Oh, I put it on the wrong one. Sorry. Filled and half-filled D-shell subshells are especially stable, but that's not the right explanation, so just don't worry about it. Anyway, if you're interested, you can look at those. Now, how you can write electron configurations, the way we have been writing it is in the order of filling. So the 4s comes before the 3d. Yes? And that's just, if you follow the diagonal rule, if you follow the periodic rule, that's going to be the easiest way to write your electron configuration. Sometimes, however, you will see them written in order of n value. And if I'll explain. There is a reason. So normally we would say scandium. Okay, here's scandium here. We would say it's 4s2, 3d1. Yes? That's the order of filling. However, sometimes you will see it written as where you put all the 3s together before you start on the 4s. So that's the order of the n value. This can be useful if you are writing ion configurations, because if you write it in this order, you remove the electrons. Like let's say you wanted to form +1 ion. You would remove a 4s electron first. Okay, if you wanted to form a 2+ charge, you would remove both 4s electrons. But if you wanted to form a 3+, only then would you take out the 4s2 and then the 3d1. It's just what you need to know. I don't know why. Okay? So when you're removing electrons, that's going to become important. But there's also another way to do it if you don't like writing them in order of n value. Okay? You don't have to write them in order of n value to figure out which ones you're taking out first. No. Okay? Here's cobalt. Here's the order of filling. Here is in order of n value. And there are people who write them in order of n value all the time, so don't get thrown by it. Don't be like, whoa, why are the 3s before the 3Ds before the 4S's? It's okay, it's allowed. You can write them that way if you wish to. Okay? Filling, in the order of filling, it's easier to write. But if you do it, this is the order of filling, easier to write. But if you do it in order of n value, it is easier to remove the correct electrons when forming cations. It is also easier to count the valence electrons. Here's bromine. You'll notice we got some P's in there. See, I've got a 4s2 and a 4p5, and I've got a 3d10. In order of n value, the 3d10 comes first, and then the 4s and the 4p come next. Okay? There's a whole table with all the configurations in order of filling. Here's a periodic table with all the configurations in order of n value. So if you're interested in looking at that, you can be like, go take a look, whatever. Now, what are core electrons? They are the set of electrons within the configuration, with the configuration of the noble gas, with an atomic number less than that of the atom being considered. So you remember when we put the noble gas in the brackets? That's the core electrons. Okay? So for silicon, the previous noble gas is neon.
So basically, it's like the far side of
Yeah. Okay, so our core is the 1s2, 2s2, 2p6, that's our neon. And then the valence electrons are electrons that can be involved in bonding. This means they are not in the core, but they are also not in filled D or F subshells. Excuse me. So, valence electrons for silicon are fairly straightforward because there's no D or F subshells. It's just the ones that are not in the core. But if we have technetium, technetium is like got 1 billion electrons. Our previous noble gas is krypton. And then it has a 5s2 and a 4d5. Is that D subshell filled? Not filled. Okay, so it counts towards the valence electrons. So how many valence electrons do we have? We have 2 plus 5 is 7 valence electrons. Now, gallium gets into a filled D subshell. So we have our core. We have a filled D subshell. Yes. And what that means is that here and here, this is the valence electrons. And this is where filling in terms of n value does give you a better picture of who your valence electrons are. Okay, because here my valence electrons are split apart when I write it in order of filling. When I write it in order of n value, my valence electrons are together. So we have our core, we have our filled D subshell, and then we have our valence. Yes? So, can those 3 d electrons be involved in bonding? No. Only the 4s and the 4p. Again, here we have lead, okay? Lead is, oh, and actually, if we look on the periodic table at gallium, let's just take a look. Gallium is here, yes? What charge would a gallium ion be? It's right under aluminum. What charge is aluminum? Aluminum is 3. Gallium is also 3. Let's go look at our structure here. Look at this. We've got 3 valence electrons. Therefore, gallium forms a 3+ ion when it loses those 3 valence electrons. Ga loses its 3 valence electrons to become Ga 3+. Do you guys know the 2 most common charges of lead? 2+ and 4+. What does it look like is happening when lead forms a 2+ ion? Which electrons is it probably losing? The 6p2 electrons, okay? And when it forms a 4+ ions, it loses the 6p2 and the 6s2. Yes, because it's the highest energy. Yeah, and that's why writing it in order of energy level is best when you're looking at the formation of ions. Okay, so we have our core. We have the filled D and F subshells, which are not valence electrons. And then we have our valence electrons. Yeah. Ooh, that's because I copied and pasted. That should say 4. Fix.
So losing 2 is still more stable than none, right?
Yes. So PB can lose its 2 6p electrons to form PB 2+. PB can lose first the 2 6p electrons, then the 2 6s electrons to form PB 4+. Does that make sense? Okay, so you have a choice to figure out which electrons are removed, because if we were to write PB, the configuration for PB 2 plus, it would be xenon. Uh, 6s2, 4f14, 5d10, and we've lost those 6p electrons. And then if we had pb 4 plus, it would be xenon 4f14, 5d10. So we lose the p's and then we lose the s's. How can you remember that? You can write it in the order of n value, or if you don't like that, you can remember that you always remove p's before the s's and s's before the d's. And if you remember, if you forget that, you will be pissed. PSD. Yeah? So you need to remove the p's first, right? Remove the p's first, then remove the s's, and only once all the p's and the s's are gone would you ever remove a d. Okay? And if you forget, you're going to be pissed. PSD. Okay? And if you don't like remembering that, then you can write it in order of energy level and you'll just take them off the end. You'll be like, I'm just going to work my way backwards and take them off as I come to them. That's the other way of doing it. Okay, so remove P before S before D. Okay. There's some orbital worksheet here. We're going to not worry about that right now. Electron configuration of ions. This is on page 120. Yes. Sorry, when what? You would only do it if you're asked to write the full electron configuration, which I will probably on your test give you 1 or 2 of those just to prove that you can do it. Do you know what I mean? But usually it's not as useful. It's kind of there to make sure you've learned it so you understand what's happening when you write the core. Yeah? Okay. Yes. Of course. Would you guys like a 5-minute break? Yes. Excellent. Okay. 5-minute break. Yeah. We're getting there. Hand sanitizer. Like this?
Is this? So the valence electrons switch places?
Yeah, so what happens is that you put it in order of the 3s come before the 4s. And so
Yeah.
that puts all the valence electrons together rather than having them split with the 3Ds in the middle,
Oh.
right? Because the bold ones are the valence.
Yeah.
The non-bold ones are not
Uh-huh.
valence because they're
Yeah.
infilled for F or D subshells.
Oh.
So
Okay.
if you write it in order of energy level, all the valence electrons will be together.
Yeah.
Yeah.
Okay. Good, thank you.
Yep. Oh my God, we're almost finished section 9.3. It's a long one. Yes. Yes. Are you trying to clean it off or something?
Please stop touching my phone.
Why did you notice this up here?
Oh, and this is.
Oh, tomorrow we're going to be doing a POGL. Would you like to make your own groups? Okay, but if you make your own groups, I don't know what I'm trying to say. Like, I just think it's good if you get to know other people. Has it been horrible getting to know other people? Sonia's like, yes, it's been horrible. I've hated every moment of it. Oh my God. No, honestly though, I cannot stress to you how important it is to go outside of your immediate peer group and get to know other people, especially as you go into university, because you're going to be in there and you're going to be like, okay, I need to now know the smartest person in this class because none of my peer group, even though they were really smart when they were in high school, none of them understand this. So we need to go find the smartest person in the class. So that means you need to introduce yourself to a whole bunch of people. Yes? And you need to find who those smart people are and be like, hey, do you know who understands this? And then I would recommend baking cookies for that person and saying, hey, would you like some cookies in exchange for helping me with my homework? And the worst they can say is no. And if they say no, then hey, you got some cookies. So, just Yeah. Okay, page 120. So a cation has fewer electrons. So that means we need to remove electrons in order to make a cation, a positive ion. Anions, of course, has more electrons. Page 120. 9.3K. 9.3K. Cations, to write the cation configuration, they're always removed from the outermost orbitals with the highest energy first. So we always remove from the highest N value. Okay? So if we want to, this is where I've got an illustration of what might happen if you don't write in the order of N value. So here is Sn in the order of filling. Our 4d10s, remember we don't touch those because they are not valence electrons. Now, if we reorder it, all of our valence electrons are together, which is nice. And we simply remove, we start at the right and we move to the left. So if we use the order of the N value, we have tin, 0. If we want to form a 2+ cation, which electrons do we take away? We take away the ones on the far right, which is the 2p, okay? Or sorry, not the 2p, the 5p2 electrons. Now we have Sn2+. What are we going to take away to get to Sn4+? We're going to take away the 5s, which is going to leave us with the correct electron configuration for tin 4+, which is krypton 4d10. If you leave it in the order of filling, it is possible to make this mistake. You could probably write the 2+ because the 5p2, you'd be like, okay, I'm going to get rid of those. And my Sn2+ is good. It's 5s2, 4d10. But you might think, oh, who's next? 2 of those 4d electrons. And if you thought that, you would be wrong. Yeah? Because you always take from the highest energy level first, which always means you're removing P first, and then you remove S second, and only then, and I don't know when this would happen, you would remove D third. Maybe if you're doing like maybe if you've artificially created an ion, okay? Like let's say that you had a lead 4 or a tin 4+ and you shot some ionization energy and you ripped off an extra electron, then you could remove a D electron, okay? It's not something that would occur in nature, but it is something that you could do to it, okay? And basically this works the same as remove highest energy levels first. Yes?
So all of the electrons in the highest energy level are the valence?
Yes. The electrons in the highest energy level, those are our valence electrons. Okay, so remove P before S before D, and if you don't do that, you will be pissed. Okay? But you don't have to remember that because you can always just be like, oh, I'm not going to remove the 4D, I'm going to remove the 5S because that's a higher energy level. Always remove from the highest energy level. Okay, so here's vanadium. And you can write it, this is the order of filling. And you're going to remove p electrons first. Well, there are no p electrons. You're going to remove s electrons second. And so you end up with vanadium 3d3. Or you can say, I'm going to remove the 4 levels before the 3 levels.
Wait, isn't vanadium like multivalent?
Yes. But if I wanted to form V2+, this would be its configuration. If I wanted to form V3+, V3+ would be argon
Oh, 3D2.
3D2.
Oh, so you don't have to lose them all then.
No, and that's why they're multivalent.
Oh.
Okay,
So the more they lose, the more favorable.
sort of, not always, but let's not get too detailed. Okay, I don't know why I have this twice. Obviously, I meant to replace it with another example and never did. Anions, we have an S2 ion. S has 2 more electrons than neutral S. So you can write this is S. 1s2, 2s2, 2p6, 3s2, 3p4. S2 minus is going to be 3p6. Okay? Yes.
Add the electrons to the highest energy.
Add the electrons to the highest energy level. And you know what? Honestly, because it's only because it's only the nonmetals and they're all really close to full, it's not really that big a deal. You're not going to have any D subshells or F subshells making things complicated. Am I going to add to a D subshell? No, because if you had spaces in your D subshell, you would be a metal and you would not be forming an anion.
Oh.
Yes? All your nonmetals are over in the P block. Yes? All your nonmetals in the P block, so you're always going to be filling up that P subshell to form anions. Okay? And you'll notice that we fill up so that this would be, all of this would be equal to row 3, argon. So it's the same as argon. Now, am I allowed to write the electron configuration as argon? No, because you cannot just write a core and then be like, okay, I'm done. Okay? No. However, I'm going to introduce you to another word. S2 minus is isoelectronic with argon. Now, if you have an isosceles triangle, what kind of triangle is that? 2 angles the same. Iso means the same. So if it's isoelectronic, what do you think that means? It means it has the same electron configuration. Okay, we're going to come across the word isoelectronic a lot more later. Okay, but generally, if you're not in the transition metals, if you're not in kind of the weird metals, over here. Usually, if you're in the alkaline metals and the alkaline earth, they form ions in order to become isoelectronic with the previous noble gas. If you're a non-metal, you form anions to become isoelectronic with the next noble gas. Okay, so your main group elements kind of behave that way. All right? Ooh, look, an isoelectronic series. How clever of me to think of isoelectronic at that time. Sulfide is isoelectronic with argon. It means it has the same number and configuration of electrons. So we can write an isoelectronic series, all the ions that have the same configuration. So our halogen, it always is going to end in something P5, right? Because they're one before the end. You're going to add one electron, so it becomes something P6. That's our halide ion. And that, once you have filled the P subshell, that's the same as a noble gas. So here we go. N3 minus, O2 minus, F minus, neon, Na plus, Mg plus, Al3 plus. Guess what their electron configurations all are? Right? Because that's what they're trying to do. But if you look at the neutral atom, if you just had N, then N is 2p3, O is 2p4, F is 2p5. Neon, of course, has it filled. So we're basically just filling that P subshell to get to the same as neon. And then when we get to our metals, past that point, we are removing electrons to get to that noble gas. So all of those ions and atoms are isoelectronic with each other. And here is our isoelectronic series, all centered around neon. Okay, N is trying to increase its level to neon, so is O, so is F. Sodium and magnesium and aluminum lose electrons to become the same as neon. Could you list another isoelectronic series? Mm-hmm. Phosphorus, sulfur, chloride, argon, potassium, calcium, and we're just going to leave it at that. What would our charges be? Phosphorus, 3 minus, 2 minus, minus, 0, plus 1, plus 2. Okay? And then there's just more chit chat about the core electrons and the valence electrons, but I think we've talked about that a lot already. Okay. Core electrons, valence electrons. Why do I have this twice? Page 123. So you're going to do 9.3J. You're going to do page 123. Those are the questions in 9.3K. And Hebden, page 157, number 28. Now, a lot of this can get really repetitive. So if you're finding that you're like, I've got it, I don't want to do every single question, for example, do every other question or every third question or something like that, yes. Okay, you don't have to do every question. And 158, number 29, H to P. Okay. Would you guys be ready to write a quiz on electron configurations on Thursday?
It's Thursday.
On electron configurations, just electron configurations. I think you'd be ready. Thursday. Huh? Be able to write electron configurations. I mean, there's not much to it, right? Like, here's an element, write its configuration. Here's an element, write its configuration with the core electrons. Here's an ion, write its electron configuration. That's it. Done. No orbitals, no nothing, just write the configuration. It's a single skill. You don't need to know about orbital shapes or anything like that. You don't need to be able to draw orbital diagrams, just the configurations. Yeah? Yeah. Hi. Yes. Okay.
Listen by a whole house.
Everybody be quiet, but 11s pay attention.
Grade 11 is just a reminder that you have to see us a lot of assignments that are due this Friday. You can help us to spread the word. If you need paper copies, they're available for help from here every day, but not tomorrow. We're on the trip. And if like bracelets can stop by.
So I'm glad you're processing because it's due Friday.
What does the Pokemon sound?
Local process oriented guided inquiry. So it's how you get your answers like that. Yeah, you should, if you're not feeling well. I know it's hard because then you miss stuff, but look after yourself.